Alright, we're going to try to use my school computer, not my home computer. Fingers crossed that it goes well. If you've not been in my classroom, this is my little cubby hole behind my desk that I sit in all the time. What I want you to do is to start off with bell work, and then I want you, after bell work, to read the little line that's highlighted. It says, describe and apply the coordinate system used to locate objects in the sky. That's actually what we're going to be doing for the next almost week and a half. Alright? We are going to focus, though, on one of the two main ways to find objects in the sky today. We're going to look at the next one tomorrow, and we're going to do a lab over the next few days looking at all of them. Our main goal is to answer this question over the next few days. So what I want you to do is write it down in your science journal. What is the celestial sphere? Basically, it's a huge, giant, imaginary sphere that, when you're looking out into space, looks as though all of the stars are, and planets, and everything in the sky is on the inside of almost like a giant bowl that's covering up the Earth. We used to think that the Earth was the center of the universe, and so the stars and the planets and everything else were not the center, and they were moving around planet Earth on the inside of this giant sphere. We don't think that anymore, but it's very convenient when you're trying to tell people where to look. The reason that that is so useful is because we can put a coordinate system on that sphere. And so if I want to explain that a star or a supernova or a galaxy or a black hole, something is going on up in the sky, I can point to it using a coordinate system that we can kind of lay on the inside of that giant imaginary sphere. That's why we use it. It's not how reality is. The universe is not inside of a giant glass bowl, but it's useful and helpful because it makes it so much easier to find things up in the sky. The coordinate system that we're going to look at today is called the horizon coordinate system. And if you guess what that is based on, it should be pretty obvious. It's based on our horizon here on planet Earth. Because my horizon and what I can see with my eyes is different than what somebody, let's say in Miami, can see, it's going to change depending on where the observer is. So it's all dependent on the point of view of the observer, which means if you're next to somebody, it's perfect. If you're not next to somebody, there's a huge problem and it doesn't work at all. There you go. So it works when you're next to somebody because you have the same horizon, but if you're not next to somebody, there's no point in using it because it is completely unfunctioning in that respect. And I'll get into why in just a minute. It uses two words, two of our vocab words, altitude and azimuth. You should have those written down, but if you don't, altitude is the measurement of height in the sky from 0 to 90 degrees, and azimuth is the measurement around the horizon from 0 to 360 degrees. So if we have our giant celestial sphere, we have this giant, I guess, bowl covering Earth, we can't see the half that's under us. We can't see the half that is below the horizon. We can only see what's above the horizon. So if I want to say, look at this star, I'm obviously looking up. I'm looking at something above the horizon. So the measurement for how far up and down I need to look, like, it starts at the horizon, and the horizon is going to be 0. I hope that is common sense. It makes sense. The horizon is going to be 0, 90 degrees, straight up. You know, it's measured in degrees from 0 to 90. That's very similar to when we were talking about finding Polaris, finding the North Star, where the horizon is 0 and straight up is 90 degrees. I was actually teaching you the horizon coordinate system. 0 degrees is the horizon, 90 degrees is, you can see, straight above my head, and then it's just measured in degrees from there. Where do I look? So altitude tells me how far above the horizon I need to look, but which direction do I need to look? Well, that is what's called azimuth. It's a word that you're never going to hear outside of navigation, outside of astronomy. Azimuth tells you which direction. It works by having north be 0. So let's say, just for the sake of this video, that north is directly that way. All right? That means for me, that way is north, and then it goes around clockwise in a full 360-degree circle. So there's 0. That way would be 90. That way would be 180. You guys are sitting at 270, all the way back to, and you can call it either 360 or 0 when you get back to facing north. Let's say if that's north, halfway between north and east, 0 to 90, that's going to be 45 degrees. And so it works just like a compass would. North, and then we have a 360-degree circle until you get back around to north. This is not a globe, okay? I don't want you to mistake this for being a globe. This is just a person floating in space, actually a person sitting on the surface of a planet with a bunch of lines drawn around them. Some of those lines correspond to things that you should hopefully recognize. So we have the meridian right here, which is a point going from directly above your head to directly below your feet. Above your head is called the zenith, below your feet is called the nadir. You have our polar axis. Remember, the Earth is spinning, but it is tilted in its spin, which is why this axis is tilted. And then we have our horizon. The horizon is straight ahead. This is where the sky meets the ground. And if you're just standing on perfectly flat Earth, the horizon is directly in front of you. This is a very similar diagram to the one that we just looked at. It's got most of the same words. You have zenith directly above this little person who's just standing, in a field. The nadir is directly below this person. The horizon is directly where their sky and the ground would meet. And you have a number of meridians going from directly above them around to directly below them. North, south, east, and west are the directions. And you can take this little star and you can drag it around. That's what makes this one different. If I put this little star over on the meridian directly north, it should be either 0 or 360. You can see it's pretty close. The closer I get down to the horizon, it gets closer to 0. I can go negative, but he wouldn't be able to see that star. I can go up to the zenith, and he would have to look directly above his head to see that, so he'd have to look up at 90 degrees. Let's say you're next to somebody and you're like, hey, person who's next to me, why don't you look at an altitude of, 71, there we go, at the azimuth of 215. We're almost there. There we go. And that's where that star is located for anybody who is next to this little person. That's how you use the horizon system. That's all there is to it. Let's say you want to talk about something that is on the east. You have to face east. It's halfway up, 45 degrees. That's where that object would be located. So, pretty straightforward. That's all there is to it. Now, what we would do in class is the pointing game. And I'd want you to point to different places. I'm actually going to do that for you and kind of show you what it would look like. All right. So if I pointed to 0, remember we said that north was that way. So if I want to point my azimuth, which is which direction am I facing, I'm going to point at 0. North is, there you go, directly that way. Next, 90 degrees would be that way, directly behind me. 180, it's going to be over there. 190, move a little bit. 360 would be back over this way. same as 0, 270, 91. Oh, that's you guys. 300. So 270, go a little bit farther to 300. I hope that translated on the video. Let's look at altitude. Everybody point to 0. It doesn't matter which direction, because I haven't told you a direction. It's just how far above the horizon. So 0, just any direction that you want. It would be straight ahead, straight in front of your eyeballs. 45, halfway up. There you go. Don't look like a Nazi. 90 degrees, directly above your head. 25 degrees. So 0, 45 is about halfway, so 25 is maybe like this. The zenith, same as 90. The horizon, straight ahead. Let me point at you guys. That would be up for me though. So straight ahead. Nadir, directly underneath me. 28.1. Where have we seen that before? That's the latitude that Orlando is at. So if I can point to 28.1, if I'm pointed north and I can point to 28.1 degrees, hey, that's where Polaris is. That's where our North Star is. So where is this little girl pointing to? Well, this star up here, if she wants the altitude, starts at 0. There's 90 at her zenith. It actually tells me that this angle is 60 degrees, so that makes an altitude of 60. What? That was easy. But what is the azimuth? Well, it says southeast. So if north is 0 and east is 90, south is 180. What's directly between 90 and 180? 135. So her azimuth is 135. An example when you could use this, if you wanted to measure where the sun was in the sky. You know that as the day goes on, from 11 to 1, from 11 to 1 to 2 p.m., 3 p.m., the sun's going to get higher in the sky. So at 11 is 60, the altitude is going to get higher at 1, and then it starts to set, starts to go back down. The azimuth, the sun's not always in the same direction either. It starts off in the morning, rises in the east, sets in the west. Now that's not directly east, not directly west, and we'll get into why a little bit later this year, but it has to do with what time of year it is. Remember, altitude is how far above the horizon something is. Azimuth is which direction am I going to be facing. Starting at 0 is north. I want you guys to make a prediction where you think that star is located. Alright, let's take a look at this star right here. Altitude is usually written first, so we'll do that first. We have the horizon, which is 0, and let's take a look from 0. Here would be 90 degrees directly over our head. It's more than halfway, it looks like. I would say maybe it's about, there's halfway, 45, about 60. It's hard to do without a scientific instrument, but we can still make a good estimate. That's the altitude. Azimuth, start at 0 is north, 90 is east. So we have, there's 45, it's less than 45, maybe about 30 degrees. So altitude 60, azimuth about 30. And let's see what we actually have. Oop, I was wrong on the azimuth. Maybe I should have looked at it before I did this. Altitude, I got pretty close. Azimuth, I had about 30. When you guys are asked to do this, you guys, there will be one very correct answer. Only one very correct answer. So as long as you have an idea of how to do this, you'll know what the correct answer is. Let's try another one. Altitude first, and we have 0, 90. I'd say this is maybe 10, 15. Let's go 15. Let's do 15 degrees of altitude. And then we have our azimuth. Start at 0 is north. There's 90, 180. There's 270. That looks like it's almost halfway in between south and west. So halfway between 180 and 270, which is 235. So let's say It's altitude of 20, azimuth of 235. I was wrong on the azimuth again. But still pretty close. Pretty close to do without a compass. I got the altitude correct as well. You guys, like I said, there's going to be a very correct answer when you guys need to do this. We'll do one more. Altitude first. It seems as though this is almost directly overhead. So we have 0, 90. I'd say this is maybe 80, 85 even. Let's go with 80. Altitude of 80. Azimuth, there's 0. And we have 90. We have 180. Let's go 170. A little bit less. So we have altitude of 80. Azimuth of 170. I was dead on with that one. So that would be the altitude and azimuth for this particular star. Alright, normally I would have you guys look around the room and find the altitude and azimuth of different things, but you're not in here, not all of you anyway, so we are instead going to just do this in whatever room you're sitting in. I want you, instead of finding the projector on the ceiling, because you probably don't have one like we do in the classroom, find something on your ceiling, whether it's a light, a fan, a bug, just anything that's on your ceiling. And I want you to do the altitude and azimuth for that object. Now that you have that, I want you, and I literally want you to do this, to get up. I want you to walk to the other side of the room, and I want you to do the altitude and azimuth for the same object. Now if you are on the other side of the room, in order to see, let's say it's a ceiling fan, if you went to the other side of the room, you're going to have to be facing in a different direction in order to see that ceiling fan, which already means that our azimuth is going to be different. If you are directly under the ceiling fan versus over in the corner, then you're not going to look directly over your head. You're going to look kind of at an angle, so your altitude is different. Hopefully you guys can see that if somebody moves, the altitude and azimuth of an object is going to change. We're going to start by looking up into the sky. We're going to see a bunch of constellations and asterisms. If we look directly over our head, we call that the zenith. If we look directly straight forward, that's the horizon. That would be 0 for altitude. The zenith is 90. Let's go about halfway up. And as time goes on, you see the clock moving. The stars are going to seem to move. That's happening because the Earth is spinning. There's one star though that doesn't move. It's right here, and that is Polaris. That is our North Star, our pole star. It's not always at the zenith, but a line that goes from the zenith down to the nadir, that's called the meridian. Azimuth starts directly north, goes clockwise, altitude starts at the horizon and goes up to 90. Your exit ticket. I want you to take what I kind of just mentioned a slide or two ago, and I want you to think about looking at that object on your ceiling, and I want you to then think about how that changed when you moved locations. Okay? Answer these 3 exit ticket questions. Would those answers be the same? Those coordinates be the same when you were in different locations? Why? Why not? Alright? And what does that mean for somebody who wants to use the horizon system as a means of telling somebody where to look up in the sky? That's your exit ticket. We're done.